Today I'm going to talk about lunar micro rovers. This is something that it's within RAL-Space. A few of us grads have been sort of tackling and coming up with potentially ways that we could maybe benefit the industry, benefit science, and do something we're kind of interested in. And we've sort of gone around this idea of micro rovers. Because it's tackleable by small teams, and there are lots of these benefits that we think that they might have over other types of missions. And this is especially for sort of science missions, which is something that RAL-Space are very big on. That's the sort of thing we do, rather than sort of commercial missions. We're very much into instruments and getting instruments into places that they need to be, and doing the right things for people like ESA and people like NASA. So just as a sort of overview, what's the definition of sort of a micro lunar rover? It's a bit like, I sort of think of it as like CubeSats. This is almost like a CubeSat rover, but micro rovers are typically sort of less than 10 kilograms in mass, and have, that's sort of the main sort of aspect that's important about it. Is the mass, but it usually means that the size is sort of the size of a shoebox, and tends to be sort of 1 to 2 U size payloads. And these have been very popular up to this point, especially with sort of X Prize winners. So people like Astrobotic have one that's going to be going to the moon very soon. But then there's also other groups such as sort of the Space Robotics Lab in Tokyo, which was an X Prize winner, and then NASA's got some quite interesting small lunar micro rover projects. But yeah, there's all these small rovers that are being developed by many groups, many small groups, and we sort of think the real benefit to these is because they're small, they're relatively cheap, especially in comparison to these sort of larger rovers, which we'll talk about in a minute. And there is the potential for potentially more risk to be taken on one of these smaller ones, and they can sort of achieve a little bit more when taken into account. So if we were to say, look at what a traditional rover would look like, and these are the ones that you see quite a lot in the news. So you have obviously these rovers such as like Curiosity, which is the size of a car. It's cost, I think the last time I looked, it was almost $3 billion. I think Perseverance is probably going to be a similar sort of cost to that. And then you also have these ones like the Chang'e 3 and 4 rovers, and then NASA Viper rover, which is planned to launch, I think, in end of 2023. And these are all really big. They're sort of car-sized rovers. They're costing $500 million minimum to build and design one of these things, and they're very complex, often having large amounts of instruments on board, because if you're spending billions of pounds or billions of dollars on a project, you want to have as much science value coming back from that as physically possible, and it makes a lot of sense. And also with that, because you're spending all this money, you also need to be more reliable. So you're generally going on this normal route of sort of ESA and NASA style large projects, where things are expensive, they're very reliable, and they're going to last an awful long time. Curiosity's lasted 15 years or so, which is amazing, but isn't always needed, especially when we think about the way that the moon is being moved at the moment. We want to be there very soon. We want to get people on the surface in by 2024. And when you're on there, there'll be lots of things to do, but they want to be done in a very short time frame. So these missions that can last an awful long time are not necessarily needed, and especially this highly complex and highly reliable grouping does not necessarily needed for these sorts of future missions. And the NASA's Viper rover is sort of going down that method by using sort of a cheaper landing system and things like that. But it's still very expensive and very large for essentially what could be done potentially with a few smaller rovers. And yeah, this is kind of key as well, that actually of those 3 rovers that are on there right now, 3 of them had to have quite large and purpose-built landers for them. Even the Viper lander using using Eclipse lander is still sort of semi-developed just for it. So there's all this very custom side of all these things. So when we actually look at what's going on the moon at the moment, and this is, yeah, this concept and what we've been looking at is very much focused on the moon, but hopefully a lot of these ideas can move to sort of other small bodies as well, potentially, you know, Mars, or maybe even sort of large asteroids or other smaller dwarf planets and things like that. But yeah, specifically the sort of instruments we talk about here are mainly aimed towards the moon and what the science is needed on the moon. And there's quite a few popular science routes at the moment going on, and this is all something that's being discussed heavily, especially by scientists in Europe and in the US. And one of the popular ones is sort of search of volatiles. We're looking for sort of water and things like that, which are very beneficial to both science and ISRU. And then you also got things like actually understanding the large scale geographic, you know, what is the moon actually made of on the small scale. So we know generally we can look at the surface quite easily. We've got lots of things looking at the surface. Is there better science that can be done from the surface to look better underneath? Also things like magnetic fields. There's a lot of great science has been looked at on sort of small scale magnetic fields on the surface of the moon. Dust and sort of particle distribution on the surface is also a massive, arguably a problem, sort of robots and human landing systems, and that's something that needs to be characterized. There's only ever been one dust detector on the moon, and that's actually, it was very fast overcome with dust, and actually there's very little understanding about what the actual makeup of sort of this regolith and how it's sort of distributed in sort of the atmosphere of the moon. So that's something that needs to be known. The radiation environment is fairly well known, but again, we've got these sort of small scale stuff that we don't necessarily understand. And then lava tubes, that's another big aspect of what people want to understand when it comes to what's happening on the surface. And we can make good guesses about where these lava tubes are, but actually going out there and searching for it is a whole different matter. And there's all these big benefits about using them for sort of human habitations. And if you look at these lists between science and ISRU, or even just ISRU and human landings, you notice that there's actually quite a lot of links there. And so there's from these missions that could solve either one of these problems, you're probably going to solve a science problem and an ISRU problem at the same time. And that's good. The other thing that sort of allowed this trend that's allowed this type of mission to sort of go forward as well is these CLPS missions. So the Commercial Lunar Payload Service, which is this something that's been developed by NASA, and quite a few contracts have gone out. I think at least 4 have been actually signed and chosen. But from what I've heard, there's potentially up to 15 over the next few years, and that's actually quite a large amount, especially when each one of these landers can hold large amounts of instruments, sort of 20 instruments potentially, quite a few hundred kilos. And that's actually something we need to take into account, and how do we use this effectively? Because there's a lot of great science that could be done on a lander, but there's also some even better science if you can get a few hundred meters away from the lander. And the thing is, as you've seen, if you look anything about sort of like the Viper rover, that Viper rover will take up one of these landers. It takes up the entire lander. So that'll be on the 4th one, whereas this 3rd lander, which is in the picture there, the Masters XL1, which is Eclipse 3, that will have something like 20 instruments on board, as well as at least one small micro rover in some form made by Astrobotic. So these are all great trends, and these are all things that need to be understood, and is part of what we have taken into account with how we're going to think about how these micro rovers can be used. So one of the key points is understanding how this science is going to be done. how you would actually do it, and whether you could actually, or whether there's already instruments out there to a certain level, sort of high TRL levels, or like 4 or 5, that could reasonably be turned into an instrument that could be flown in the next 3 or 4 years. And this is sort of where we've focused our initial level of research into this. So we've got a few example payloads from different places, and why they're kind of important to understand this science. So the first one would be ground penetrating radar. We're talking about being able to look at the sort of near surface and understanding the sort of geological makeup of the surface. And this is quite important because, especially when we're talking about ISRU and human landings, you want to understand what you're landing on, and you want to understand that the ground underneath you is safe, and there's not, a big lava tube underneath you that's going to collapse when you put a few hundred tons of human habitation on it. And actually, ground penetrating radar nowadays can be quite small. You've got this RIMFAX instrument that's on the Perseverance rover, which is it's quite heavy. It's quite power hungry, but it's also quite small. And that's something you've got to take into account, that is quite heavy. But there are developments you can do on it to make it maybe less powerful. You could quite easily sort of reduce the power of the antennas and still have a reasonable understanding of sort of what you need. So that RIMFAX is looking for quite large distances below the ground and quite high resolution, whereas you don't necessarily need that for some of the moon activities. So you have JPL developing this mini GPR. There's a lot of instruments that we talk about on this that have mini in front of the name. Just they kind of gives an idea of what these sort of instruments are for. But yeah, this mini GPR ground penetrating radar is a good example of something that is sort of TRL4 that could be used as quite a good payload on one of these micro rovers. Next, you have sort of neutron spectrometers. So this hits the great hit of volatiles and looking for water. Neutron spectrometers they're still a remote instrument, but at the same time you're still measuring something a lot closer. So you have neutron spectrometers at the moment, or soon to be on these missions. So there's an instrument on Lunar HMAP, which is this mini neutron spectrometer that's going to be looking for water, but it's going to be looking from orbit. So what about if you could take that and put it on a micro rover and look for individual hotspots of where water could be? And the key is that you take these hotspots, and you could then, once you've found these great pools of water that you potentially know where they are, you can then get your larger rover with the big fancy acquisition systems and drills and things like that, and take it to the place where you know something is. And at that point, you've not wasted your time, essentially drilling somewhere that you know is unlikely to be, or driving to somewhere that's unlikely to be. And as well as that, this using a micro rover first to go out and scout for this information is kind of the point of what we're trying to say here, and trying to kind of show what this architect is for. Is you take one of these instruments and you can send it out to take some readings, with a fairly high risk that it might not survive it, for very long. But at the same time, you've got that valuable information that you've not had to risk a very expensive, very large rover for. So a neutron spectrometer is a great example of that, and that they've been used on quite a lot of different missions. So the Viper rovers got one on. There's a couple of sort of CubeSats and small sats that are going to be using them. Like I say, Lunar HMAP. You've got Lunar Trailblazer, which is one that Raoul's involved with. You've got the Lunar Ice Cube nanosat. And also you've got the Lovely X rover, which is an ESA one based. So I think that's also a potential one for the future. Another sort of smallish size rover that we'll talk about a couple of times here. But yeah, usually when it's on a large mission, it's a very passive instrument. It does not drive sort of. You don't go somewhere just to measure the neutron density at that particular spot. You go there for something else, and it just happens that you're reading neutron information while you're there. And yeah, the mini neutron spectrometer by ASU is a good example of one that you could use in this situation. In fact, the one that was on the Lunar H map is probably small enough, but as you can see, it's sort of got many redundant sensors, which you might not want on this mission. So yeah, another one which is actually quite a popular one and we quite like is Lib spectrometers. So if anyone's looked at Curiosity, the thing that I've always thought was the camera is actually not a camera as such, or it kind of is. There is a camera in it, but the big eye is actually this Lib spectrometer, and it's actually the laser that fires at the ground and looks at the light that's come back from this plasma that's created. And ChemCam is a huge instrument. You know, it's 30 odd watts. You know, it's very, very heavy. It's very large. But that's because there's a lot of redundancy there. And again, it's something that's designed to last a long time and is very rugged. But there are versions that are smaller and that don't need to be quite as big. And you can take away some of these extra bits you don't need. You might not need autofocusing. You might not need another camera or another complex camera to add too much context. Yeah, and you might not need to actually even have extra optical heads or extra spectrometers in there. There are all these things you can take away or add on depending on what you actually need for that particular reading you're trying to do. So again, this could be great for if you had your big rover with the big acquisition system, you're sending this out to take some readings first of a particular interesting site before you send out your very expensive people or even actually humans. Also, you've got magnetometers. Like I said before, that there's some great research. I saw a great talk the other day by some guys at RAL Space that are looking at sort of low-level magnetic fields on the surface that are actually affecting dust in different ways or affecting the surface in different ways. And these low magnetic fields are actually having huge impacts on the way that radiation is hitting the ground, which is super useful for when you're building places to live. You need to know where these things are. Sorry. Yeah, and in this case, there are a few different types of instruments. There's always more developments, but they're these top of the range sort of magnetometers that can be used and they're used in CubeSats at the moment that we could use on these sorts of missions and be within the requirements that we're sort of seeing. And on top of that, there are many other ones. Ones that I've seen within RAL Space are small cameras that can be sort of fitted onto CubeSat size things. These different micro imagers. There's these electrostatic analyzers. So all these neutron analyzers, all these small instruments, and there's loads of them being developed, especially around sort of dust detectors. We're developing one within RAL Space that hopefully we'll be able to talk about soon that is very small and hopefully looking at sort of lunar dust and the way that rovers are kicking up dust. But there's also ones about how dust actually lands on surfaces and how that the electrostatic charge on things are sort of going to build up. And NASA's actually put out quite a lot of these small payload sort of calls to try and find out what can be built. And we're going for one of them, which is going to be really interesting. So yeah, there's a lot of instruments that could sort of derive from this, and this is from sort of lots of research. We've looked at lots of very small instruments, and there are also ones that are too big. There are ones that are bigger than sort of 2U, and hopefully could be integrated onto slightly larger rovers, but are not maybe useful for micro lunar rovers, which is important. So from all this information that we've sort of got together, we've sort of developed these design drivers and what we think is important going forward, especially for these developments. And how we take this and put it into actually flight hardware, if you like, and what we need to think about. And from all these instruments, you can almost come up with a sort of baseline instrument that you can say, right, this is what we design our rover to. We can then slot in something afterwards, almost like on a CubeSat. If you were to develop a CubeSat, you'd literally go to a CubeSat manufacturer and say, right, I've got this 2U instrument with this amount of power and this weight. What can you do for me? And I have these slight requirements. could you do that with lunar micro rovers? And actually, you don't have to do all those developments. You don't have to do you don't have to come up with the platform. You don't have to come up with the way of landing. But there are there are these few design drivers that we think we need to think about in these developments. So this is mainly sort of around standardization. So things like an electronic bus, it would be really useful if everyone sort of agreed on what sort of electronic bus. And actually, CubeSats already have this. So if you have this electronic bus that's almost defined off of some of the CubeSat standards, that would be a huge benefit to the sort of industry. And also how we pre-flight test these things. Every rover has a very different way of testing what it's going to do. And actually, sort of, we want to really standardize that. As well as that, thermal materials, that's a well-known problem at the moment, and people are developing it, but how do we create these materials that small rovers could use to get these major temperature swings? And also the software side, where we're talking about semi-autonomy, that you want a lot of these things to be done on its own or in swarms. But what requirements, what services are actually going to be needed? And lots of them are already in development or have already been sort of assigned. Landing systems which are already available, but also communications architectures that, apparently Nokia the other day got a contract to put 4G on the moon. But there's all these ideas about lunar Wi-Fi and such that we need to take into account with services, and also high quality surface mapping. At the moment, we have high quality, but we don't have high enough, especially for sort of robot lower.
Just as 3 minutes are left.
Yep. Just I'm not too far away. I got to the conclusion. There are lots of instruments that we could be used, especially on this sort of baseline type rover and this type of architecture. And we would sort of baseline it as sort of a 2U, 2 kilogram, 10 watts is the maximum. In fact, 10 watts might be a little bit much, but I think that's a good way forward, especially for developing your own rover. And there's a huge amount of benefits. Like I said, missions can always be tailored to the instrument. So you have something like the ground penetrating radar, you can decide where you go. You're not using it as it's not just a backup. It's not just there for wherever you go. You have a reading, just happen to have it just in case. This is the ground penetrating radar will be the defining part of how you decide where this rover goes and what it does. But also because it's cheaper, you can increase the redundancy and have more rovers. And also if one rover breaks, it doesn't mean you lose all your instruments. You have other rovers with your other instruments on board. And for the same money, you can visit more places, achieve more and more specific science with taking more risk. Because large rovers might not go up certain inclines because they're worried that they're going to break, and they're going to break all these other instruments that they spent a lot of money on. So yeah, all these high risks is all super relevant, and the key thing that I think we've come out with is standardizing these systems are much more useful for us to be able to develop these instruments for these applications. And then we can continue and up the technology readiness level of all these individual technologies. So yeah, thank you. Is there any questions? I've probably talked a bit fast.
Yeah, thanks a lot, Ryan, for the nice talk. For the questions, please write them in the chat. I don't see one right now, but honestly, I have one. I really like the idea of the CubeSat analogy. Are there already, let's say, slots or infrastructure on the next landers, or is there anything planned from the people that want to land something on the moon?
So as far as I know, Astrobotic are the only ones that have actually got rovers planned to go on the moon that are not NASA, if you like, because the Viper rover is an actual NASA rover, whereas Astrobotic is a private company that's developed it and then asked NASA to be a part of these missions. So yeah, they have a couple. They have the Moon Ranger and they have the Cube rover. and both of those I think have sort of elements of this sort of CubeSat style stuff on it. But yeah, understanding the standardization of that is really important. In fact, I think there was a talk at the start of the week by Astrobotic on sort of a similar subject and about their lunar rovers, which I thought was really important. Does that answer your question?
Okay, yeah, indeed. And I would have a follow-up. For the communication and control of these rovers, would you kind of depend that the lander brings the infrastructure to relay your signal? You were speaking of lunar Wi-Fi and so on.
Yes, so so that's actually quite at the moment it's kind of standardized that landers have these large communication arrays, and actually NASA's come up with a few good sort of definitions for requirements for payloads in terms of how much data you can get or how much data slots you can get. So I think that there's not that huge amount of a jump to get to a point where we can understand what these communications architectures might look like. But yeah, the landers would have the main sort of Earth to Moon links rather than these small rovers. These small rovers would probably more likely have something on the sort of 2.4 gigahertz scale. Sort of, we talk about lunar Wi-Fi, but yeah, it might be Zigbee, it might be whatever else that everyone depends to start using. But yeah, it seems to be 2.4 gigahertz systems are going to be the way to go on this.
Okay, thanks. Then we have, I think, time for one more question. There's one from the chat. It's about what are the key technologies needed to make this micro rover technology a standard add-on for larger missions?
So I think the key technology is actually, because the hardware sort of exists, it's not that, a lot of these X-Prize companies have already done the hardware. I think the software seems to be something that needs to be made more rugged. That on Earth, you've already got these technologies that can self-drive rovers and cars and such, but having that rugged enough for a space mission, for something that's costing, you know, although it's not hundreds of millions, it's going to still potentially on the tens of millions scale to start with. So yeah, especially the software and like we said before about the thermal instruments or the thermal aspects of these materials really needs to be nailed down. But I think that's something that's significantly improving in the last few years.